Even before its launch, AMD's upcoming RDNA3 GPU architecture is providing a lot of entertainment. I have never seen the rumor mill working so hard, but now it seems like we've finally struck gold and the true specifications of AMD's next-gen Radeon RX 7000 graphics cards are actually revealed. To give some context to the whole RDNA3 story, we will first take a look at the leak and rumor history, and I will explain why we actually had all the right information from the very beginning. We just couldn't see it. Next, we will talk about the leak from Angstronomics, which we will then, of course, analyze in more detail and talk about the possible design goals AMD has for RDNA3. If you already followed the RDNA3 rumor mill over the past year or already know the new leaked specs, just use the chapters in the video to get to the parts you are most interested in. Without further ado, let's dive right in. It actually seems crazy, but first rumors on RDNA3 appeared over a year ago, in July of 2021. And even back then, one thing was clear from the very beginning. RDNA3 will be a chiplet-based architecture. A mix of leaks and the resulting discussions on Twitter and the Beyond3D forum very quickly created a consensus of how AMD's next-gen GPU generation was supposed to look like. So-called graphic core dies or GCDs produced in 5nm, which contain all the shaders and logic for the graphics computations, would be connected by smaller multi-cache dies or MCDs produced in 6nm, which would make up the Infinity Cache. The two top chips, Navi 31 and 32, were supposed to be based on this new modular design, while the smaller Navi 33 die would still be a monolithic 6nm chip. And to be frank, much of those early leaks and rumors still hold up today, at least when it comes to the major design choices, like the combination of 5 and 6nm chips or the monolithic design of Navi 33. Only the specs within these parameters have changed over time. Back in July of 2021, the rumors predicted a huge increase in shader count. While a full Navi 21 chip, as used in the RX 6900 XT for example, has 5120 ALUs, Navi 31 was supposed to be based on two graphic core dies with 7680 ALUs each. That's literally 3 times the amount of shaders Navi 21 has and would have been an absolutely bonkers generational increase. But it kinda makes sense back then, if we look at AMD's other developments. Let me explain. RDNA GPUs are following a very similar pattern compared to AMD's Zen CPUs. Just like the original Zen architecture, the first RDNA architecture was a huge step for AMD. It wasn't enough to win in raw performance, but it came really close and put AMD back on the map. Then Zen Plus and as such RDNA2 made another big step. AMD ironed out the kinks and suddenly could compete in the very high end. And then with Zen 2, AMD introduced their new chiplet architecture and they used it to literally double the core count in the desktop market, taking the performance crown with brute force of 16 CPU cores, enabled by the chiplet architecture. So with the knowledge that RDNA3 was supposed to make the same step as Zen 2, introducing chiplets, the assumption that AMD would bury Nvidia by tripling the amount of shaders made a lot of sense at the time. It just followed AMD's previous chiplet implementations. The same can be said about the memory interface and Infinity Cache rumors, which initially predicted the same 256-bit interface as in current-gen RDNA2 GPUs, but combined with a much larger Infinity Cache with up to 512 MB. It was just another logical conclusion based on previous developments. With RDNA2, AMD had shown how efficient a large cache is at absorbing the negative impacts of a smaller memory interface, and as such it only made sense that AMD would keep the cheap and efficient 256-bit bus and offset it with a huge amount of cache. In a nutshell, the early rumors were based on a lot of correct information, like the chiplet architecture and even the shader count for Navi 32, but then filled in the blanks with logical conclusions which turned out to be wrong. I am of the opinion that the initial leaks basically had every information needed to come to the right conclusion, only nobody thought of it. RDNA3 was supposed to become this huge shader and cache monster with a design focus on raw performance, all made possible by AMD's chiplet magic, like we have seen with Zen 2. That's why everyone was blinded by the idea of multiple graphic core dies with lots of shaders and a huge Infinity Cache. To understand why I think the initial leaks were actually right, but just interpreted the wrong way, we have to first look at the most recent and very likely correct leak from Angstronomics, I have linked the article down below in the description if you want to check it out for yourself. Angstronomics got straight to the point and published what they claim to be the detailed specs of Navi 31, 32 and 33. The big new reveal in this leak, in my opinion, isn't the shader core count or even the infinity cache size. It's the way how AMD is choosing to implement their first chiplet-based GPU architecture. While all previous leaks assumed that both GCDs and MCDs would be chiplet-based, it appears that only the MCDs are actually chiplets, while the GCDs are individually designed for each RDNA3 GPU, which basically means that Navi 31 and 32 are in part monolithic. According to the article, Navi 31 will use a 308mm² GCD fabricated in 5nm with a total of 12,288 ALUs. The GCD is specifically made for Navi 31 only and thus not a chiplet design in itself. This GCD is then combined with 6 37.5mm² MCDs fabricated in 6nm, each containing a 64-bit memory interface and 16 MB of infinity cache. This means in total, a full Navi 31 chip would boast 12,288 shaders, a 384-bit memory interface, and 96 MB of infinity cache. Navi 32 uses the same partial chiplet approach. It's based on its own 200mm² 5nm GCD, which contains 7,680 ALUs, and then adds 4 of the same MCDs as used in Navi 31. A full Navi 32 chip would have a total of 7,680 shaders, a 256-bit memory interface, and 64 MB of infinity cache. Last, the monolithic Navi 33 chip combines 4,096 ALUs with a 128-bit memory interface and 32 MB of infinity cache on a 203mm² monolithic die fabricated in 6nm. These specs are really unique and there is a lot of detail to uncover, but first let's compare them to the initial leaks and figure out why I think they basically match. If we compare the initial leaks from July of 2021 with the specs Angstronomics just dropped, it's easy to spot the similarities. A combination of 5 and 6nm dies for the top 2 chips? Check. A monolithic 6nm die for Navi 33? Check. A 7,680 shader GCD? Check. 2 of these GCDs used as chiplets for Navi 31? Wrong. That's where the information is starting to diverge, and I think I know exactly why. I already talked about how AMD has used chiplets to double the core count with Zen 2. When we look at AMD's processor design philosophy, the whole idea is to produce one single CPU chiplet and then use that chiplet to scale the entire CPU market. It's a single tape out and AMD is able to base almost all of their CPUs on this one chiplet design. It's a genius approach, but it doesn't come without its drawbacks. Latency outside of the individual chiplet is not great, which means latency-dependent applications don't perform well when they migrate across different chiplets. And that's also the biggest problem when it comes to creating a chiplet-based graphics card architecture, especially since GPUs are more latency dependent than CPUs. I even made a video back in February where I talked about a AMD patent that described a multi-chip GPU, and I used that patent to describe how RDNA3 could look like. Now we know that this patent will most likely take at least another GPU generation to become reality, but at the time, it made perfect sense. It is not impossible to link 2 GPU chiplets with a high bandwidth and low latency connection. Apple's M1 Ultra is testament to that, which combines 2 M1 Max chips with a mind-blowing 2.5 TB per second using TSMC's integrated fan-out local interconnect. And while AMD has access to similar TSMC technologies, I assume they are just not yet ready to create a GPU architecture that is fully chiplet-based. As a result, they went with the second best option, a partial chiplet design with the focus on tiny multi-cache dies and minimizing 5nm usage. And that's where the original leaks went wrong, because we assumed the goal is to reduce the number of tape-outs and scale the entire GPU lineup with as little chips as possible. That's why the assumption that the GCDs will also be a chiplet design was made, when in reality it only applies to the MCDs. The initial leaks even had the Navi 32 GCD spot on with 7,680 shaders. But when you think it's a chiplet design, it makes sense that Navi 31 would use 2 of the same GCDs for a total of 15,360 shaders. No one thought that Navi 31 had its own individual GCD. I would not continue to harass my sources, if I had any, for the specs of a Navi 31 GCD if I'm convinced that it doesn't exist. I think the early leaks got the proper specs of Navi 32 and then tried to guess how Navi 31 would look like based on the false assumption of a full chiplet integration. It's the same with the memory interface and the Infinity Cache. If I know the specs of the smaller chip and I know Infinity Cache and 3D stacking exists, I would have also guessed that Navi 31 uses the same 256-bit interface, just with a lot more cache on top. As you can see, getting the proper information is one thing, and interpreting it correctly is something else entirely. Now let's take a closer look at the Angstronomics leak, try to figure out how close it is to the truth, and discuss AMD's possible design goals with RDNA 3. I will start with the smallest of the bunch, Navi 33. At first glance, Navi 33 looks like any other entry-level GPU, with its 128-bit memory interface and the rather small 32 MB of Infinity Cache. The die size is actually supposed to be really tiny at only 203mm², and Navi 33 is still based on TSMC's N6 node, which is an optimized 7nm design. But then this tiny chip is supposed to contain a huge amount of shaders, 4096 to be exact. To understand how much that is, let's compare it to its predecessor, Navi 23. While Navi 23 is still manufactured in TSMC's N7 node, keep in mind that N6 offers only up to 18% more transistor density. It is not a full node shrink like N5. Navi 23 has only 2048 shaders. That's half of what Navi 33 is supposed to offer, and both chips use the same 128-bit memory interface with 30 MB of Infinity Cache. And even with half the shaders, Navi 23 has a larger die at 237mm². The improved density for N6 could explain the smaller die size, but not with doubling the shader cores at the same time. So what's going on here? One explanation could be that the die size that's being reported is simply wrong, and the actual Navi 33 will be larger. We have to remember that while the leaked specs do make a lot of sense, and Angstronomics offers a lot of detail that points to its validity, these numbers are not official, they could be wrong. Another option, and what I personally believe, is that Navi 33 uses a slightly different architecture compared to Navi 31 and 32. It's still RDNA 3, no doubt, but much like Zen 4C is offering a more dense and space-optimized version of the Zen 4 architecture, this RDNA 3M for mobile, that's how I would call it, could offer a similar approach. Even before the Angstronomics news dropped, Twitter leaker Kepler shared a really interesting piece of information. According to his sources, the compute units in Navi 33 and the upcoming Phoenix Point APU are slightly different to the compute units in the larger RDNA 3 chips. Angstronomics even writes that Navi 33 is not only an entry-level desktop GPU, but specifically targets laptops and is drop-in compatible with Navi 23, allowing OEMs to quickly update their current notebook designs. I think RDNA 3 in general is a already very space-optimized architecture, as AMD is targeting smaller chips with high yields to gain an economic edge over Nvidia. Angstronomics claims that a RDNA 3 workgroup, which packs twice the shaders, is smaller than an RDNA 2 workgroup. And the mobile-focused chips of RDNA 3 like Navi 33 and the Phoenix Point iGPU are even further space-optimized, for example with smaller vector register files. Of course, this also means that the IPC of RDNA 3M in Navi 33 and Phoenix will be below that of the full RDNA 3 architecture. But if AMD can pack a lot more shaders into a smaller die, it's a very beneficial trade-off in my opinion. I think there's a good chance that Navi 33 is actually tiny compared to not only other RDNA 3 GPUs, but also its predecessor Navi 23. Keep in mind that Navi 33 will most likely outperform a RX 6600 XT by quite a lot. It could even beat a RX 6700 level GPU, depending on clock speeds. Angstronomics points out that Navi 33 outperforms the top Intel Alchemist ACM G10 chip at half the die size and less power draw. But as you know, I have already talked in depth about the failure of Intel's Arc GPUs, so I'm not gonna go into more detail right now. Next up is Navi 32 with its 7680 shaders, a 256-bit memory interface and 64 MB of Infinity Cache. The 5nm GCD is supposed to be 200mm² in size, and then 4 6nm MCDs are added, with a die size of 32.5mm² each. In total we have 200mm² in 5nm and 150mm² in 6nm. It does have a larger combined die size than its direct predecessor Navi 22, but also 3 times the shader amount and a larger memory interface. So the better comparison is actually Navi 21. This of course is in part due to the switch to 5nm for the GCD, but also general density improvements of the RDNA3 architecture. Navi 32 will definitely outperform Navi 21, and depending on the clock speeds, it could be a rather large performance leap. With faster GDDR6 memory and a optimized Infinity cache, memory bandwidth most likely won't be a limiting factor. AMD has apparently spent a lot of time and effort improving their Infinity cache design, which allows them to use less cache, but more on that in just a minute. The top die is Navi 31. It combines a 308mm² 5nm GCD containing 12,288 shaders with 6 attached MCDs, which adds up to 225mm². All in all, the die size of a full Navi 31 chip would be 533mm², which is in fact a bit larger than Navi 21 at 590mm². But of course Navi 31 has 2.5 times the shaders, a 50% larger 384-bit memory interface, and only a slightly smaller 96MB Infinity cache. The die size of the GCD looks fine to me again. We see a combination of the density improvements for the N5 node and the more space-efficient RDNA3 architecture at work. Navi 31 should be at least 2 times as fast as Navi 21, but of course performance estimates are always hard to predict. Something that is more interesting to me is the size of the MCDs and the overall reduction of Infinity cache across all Navi 3X chips. The MCDs do seem rather large for what they are supposed to offer, a 64-bit GDDR6 memory interface and only 60MB of cache. Locusa did some great RDNA2 die shot analysis where he estimates the actual chip space the individual parts of the GPU use. For Navi 21 he estimates 6.3mm² for a 32-bit interface and 44.6mm² for 64MB of cache. If we take these numbers and try to estimate the size of a 64-bit interface and 60MB of cache in N6, the 37.5mm² of each MCD seems way too large. It should comfortably fit at least 32MB of cache, in addition to the 64-bit interface. So what's the reason for this discrepancy? Of course it could be again false data, either on the die size or the cache amount of the MCDs. But I think the Angstronomics Leak is mostly correct, and there are some interesting reasons why the MCDs could be larger than the corresponding parts in RDNA2. First, the MCDs need to connect to the GCD, and as such, there needs to be a silicon space reserved for the interconnect. Second, it is very likely that the MCDs are already prepared for 3D stacking, similar to the 3DV cache on Zen 3D. Apparently, AMD is experimenting with stacked Infinity cache on top of the MCDs, which would at least double the amount of available Infinity cache. For this purpose, each MCD has to include space to bond with a TSV connection, which also increases the die size. And yes, AMD might not use 3D stacking for RDNA3 at all, or only at a later point, but they would still include this feature for every MCD, just like every Zen 3 die has TSV connection points, even if only the 5800X3D actually uses them. AMD has to reserve space for the interconnect to the GCD and a possible 3D stack cache. On top of that, it is very likely that AMD has optimized the cache cells used for the Infinity cache to offer more bandwidth and better latency. Angstronomics goes into more detail with what they call memory attached last level. These improvements also increase the space needed for each block of cache. I think all these points are a good explanation why the die size of the MCDs seems a bit large compared to what they actually offer. One thing that I want to mention is the amount of workgroups each RDNA3 GPU has. Navi 33 starts with 16 workgroups, Navi 32 is supposed to have 30 workgroups, and the top dog, Navi 31, increases that to 48 workgroups. Maybe you noticed the same thing I did. It's a kinda odd increase in workgroups. Navi 32 only having 30 workgroups instead of 32 sticks out like a sore thumb. There might be a good reason for that, but I also wouldn't be surprised if Navi 32 will have 32 workgroups. 16, 32, 48 would make a lot of more sense if AMD is using 16 workgroups as a base design for RDNA3. RDNA3 is shaping up to be a really interesting architecture, and from my point of view, AMD is focusing on a very clear design goal: performance per square millimeter. As you know, new process nodes are getting exponentially more expensive, and at the same time, AMD is still supply constrained, because bleeding edge nodes are highly thought after with many competitors taking huge chunks of the available volume. What good is an amazing GPU on paper if it's in short supply, like we have seen over the past 2 years? And while shortages result in larger margins, AMD still wants to grow their market share. With RDNA 3, AMD is creating super cost-efficient GPUs to combine the best part of a monolithic and a chiplet design. Just take a look at Navi 31 and 32. The compute units are located on a monolithic die, which allows for the best possible performance without latency issues. Not only did AMD trim their compute units for space efficiency, these so-called graphic core dies are also produced in TSMC's new N5 process node, which allows for a really dense chip with great power efficiency and high clock speeds. AMD is producing the most important parts of the GPU in the best available process node. But then AMD adds the multi-cache dies, basically outsourcing the memory interface and the infinity cache. Since the cache works as a buffer for the memory controller, these two important parts are also on a single chip and can communicate efficiently. In addition, physical connections never scale really well with node shrinks, so having the memory interface on an older node doesn't hurt. The smart part is that the MCDs are produced in the more mature and much cheaper N6 node. A 37.5mm² small die will have near perfect yields, allowing AMD to produce these parts at a very low cost, and at the same time they can use all of their allocated N5 capacity for the important GCDs. If Nvidia's Lovelace 8102 really turns out to be a monolithic 5nm die with a size close to 600mm², Nvidia could be in a lot of trouble if they want to keep their competitive margins. Of course, AMD has to connect each GCD with 4 to 6 MCDs, which will be done using TSMC's advanced packaging. For RDNA 3, AMD will most likely use a 2.5D approach, which TSMC calls Integrated Fan-Out on Substrate, or InfoOS. This packaging type does not use a silicon interposer. The connections, you can think of them as tiny wires, are actually fanned out from the individual chip, just like the name indicates. It's a very cost-efficient packaging method to not add a lot of additional cost. I would like to go into further detail how fan-out works, but for that I have to spend more time on research because I'm not into that matter myself. If you have more information on fan-out packaging, let me know in the comments. A architecture can have many different design goals. You could go for pure performance, a large chip with high clock speeds. You could favor efficiency and design a wide chip with low clock speeds, close to the sweet spot of the silicon. Or you could optimize both the graphics architecture and its layout for performance per square millimeter. RDNA 3 has a single clear focus: smallest possible chip design while still competing in high-end performance tiers. It looks like RDNA 3 is a major new architectural step and not just an evolution of RDNA 2, and I'm really looking forward to its release later this year. One thing that I'm still curious about is AMD's ray tracing implementation. I have no doubt that it will be more sophisticated than RDNA 2, but the question is by how much? Nvidia will very likely stay ahead when it comes to tracing those rays. Now I would like to get your input on the whole RDNA 3 leak situation. Do you agree with me that the early leaks basically had all the right information, but we used it the wrong way? Do you think the Angstronomics Leak is on point, and what is your opinion on AMD trying to focus on space efficiency? Let me know down in the comments below. I'm looking forward to your input. I hope you enjoyed this video and see you in the next one.